Yes,
Yeah.
that's good.
Yeah.
Okay, so today we have our fourth module. So we have module 4. We will be talking about the design of steel members or steel elements for tension or compression or flexure or shear. So there's 4 types of member under tension, member under compression, member under flexure, member under shear. So each type of applied forces or applied actions has different procedure in the Australian standard. So we'll go through them one by one, and we will give some time at the end to practice a problem for each one. Okay, so this is our topics today: tension members, compression members, bending member or flexure members, and shear. Okay, so let's start with the tension member. So here's just some like description of the tension behavior. Anyway, if we have a look on this curve, there's a relation between the load and axial tension. So as you know, steel is a ductile material. So the behavior of the ductile materials is something like this. So we have first part is linear part or elastic part, and then at the yield point we have some stable behavior. So this part is called plastic, and after that we have a part of strain hardening behavior. So the strength or the stress increased a little bit until we reach the maximum capacity or the ultimate load. So we have yield point, ultimate point, and then after the ultimate start of fracture of the steel, so the load start to drop until it fracture at the final point. So at this stage, the steel has fracture. So this is represented by this point. So these are the tension, the behavior of steel under tension. I think we have talked about this before. And here's some example of in this figure axial forces in the cable stayed bridge. So as you can see, this is type of bridge. So we have this like pylon, and from this pylon we have some cables to support the floor deck. So these members are under tension. So this also type of tension member we can have. Okay, steel. This is a steel cable of one of the example of the member under tension. Okay, so let's go directly to. We can have a quick look on this part, but let's go to directly to the important part, which is design for tension, for axial tension. The design of axial tension in the Australian standard AS 4100 is clause 7.1. So a member subject to design axial tension in star. So if we have a member under tension, so the force in the member is pulling the member. So this force is called N star or NT star. This is the tension force applied. So to design for the member, we need to satisfy this condition, which is N star less or NT star less than or equal phi NT. Okay, so we have two parts. We have NT star or N star, and we have another term in phi NT. NT star is the applied forces or the applied tension, because this will be important for other types of member as well. So we have two terms, the applied tension. The other side will be the capacity of the member or the member capacity. So to make the design safe, we need to make sure that the applied tension or the applied forces less than or equal to the capacity of the member. So when we satisfy this condition, this means that the design is safe. So here in this type of members under tension, we have a tension force and we need to find the capacity of the member to compare to the tension force, where phi is called the capacity reduction factor, which is equal to 0.9. So phi is a factor of safety here in this type of design. Okay. NT is called the nominal section capacity of intention. So NT here is the nominal section capacity of the member intention. So our rule in the design is to find the value of NT. So nominal section capacity shall be taken as the lesser of the yielding of gross section. So we have two values, and the fracture to the net section NT equal to 0.85 KT times AN times FU. So we have NT equal to the lesser of or the smaller of two values. One value is A gross times F yield. The other value is 0.85 KT times AN times F ultimate. Okay, what is the difference between A gross and A? In A gross, if we have section, as you know, the sections in steel, sometimes we need to add some bolts. So if we have bolts, so you need to make like hole in the bolt. So if we look at the plan, so we have some holes. So the cross section area before the holes, or because some areas or at some places there is no holes. Okay, so if no holes, the area is called A gross. The area at the holes is called area net. So here is area net. Anyway else, so it is called area gross. So which one should be bigger, area gross or area net? Area gross all the time will be bigger than area net. Okay? Because area net is equal to area gross minus the area of bolt holes. So here we know that the definition of the terms, we have area gross is the gross section area. For example, if we have a section BD, so area gross will be equal to B times D. If Fy is the yield stress of the steel, depending on the steel grade. Kt is called the correction factor for distribution of forces, will be calculated using this clause. Area net is the cross section area, which is equal to the gross area minus the area of holes. Fu is the ultimate tensile strength used in design of steel, so this also depends on the steel grade. Okay, the factor 0.85 accounts for the brittle failure at the net section due to the holes. It is not necessary in the ductile failure because we have sufficient yielding. So that's why in this formula we have 0.85. In this formula we don't have 0.85. Okay, so if we are designing for tension, we will need to find this one first, the first NT and the second NT value, and select the smallest of them, and then our final phi NT need to be compared to N star. Okay, is there any problem with that?
No.
So here is an explanation of the distribution of forces for the factor Kt. So at the end connection providing uniform force distribution, we can take Kt as 1. The tensile force is distributed uniformly to a tension member So the tensile forces is distributed uniformly to the cross section. So all the cross section has same value. The interconnection shall be made to each part of the member and symmetrically placed about centroid axis. So again, the resultant of the force should be at the centroid so that we avoid any eccentricity in the member. Each part of the connection is proportion to transmit the maximum design force carried by the connected bar of the member. So this all some like notes to be considered when applying the force. Just have a look on that. In some cases, we have connection that doesn't provide uniform force distribution. So in this case, we need to design the member subject to combined action and kt equal to 1. So in this case, if the force, for example, is not applied in the centroid, somewhere here, so you need to move or transfer the force to here. To transfer the force, you need to apply a moment. So instead of eccentric force, we will have a force and a moment. This is not our case, but just in case you have this case, so you need to design for uh, like two straining action, which is the tension force and the moment, not only the tension force. Okay, for I section and channels, symmetrically rolled or built up section, we have to take KT as 0.85. So KT equal to 0.85 for I sections. Okay, and this picture define the value of KT. So if we have angle, so the stress will be uniform. So we can take KT as 1. If we have this type of connection, the angle is a bit not centered to the blade, so we have KT equal to 0.85. For this built up section or this I section, so the stress will be distributed like that, so we can take KT as 0.85. So this is just some explanation of the value of KT. And here is, you can take the value of KT from this table, from the Storian standard for T100. So depending on the configuration of the end connection you can take the value of KT from this table. So for unequal angles, KT 0.75, otherwise for angle 0.85. This case, if you have two angles, take it similar to the first case, so 0.75 or 0.85. Here, if you have channel, so we have 0.85. If you have this T section, so we have 0.9. If we have this two symmetric angle in this way, so take it as 1. Two channel, 1. Two T as 1. So these three cases, we have symmetric connection to the blade or to the other member, so KT equal to 1 for all cases. Otherwise, you can take it 0.75 or 0.85 or 0.9. Okay. Now let's have a look on how to find area net. So for tension member with holes, and usually all the steel members, bolted, should have holes, because if you need to connect two members together, you will need to connect them with a bolt. So this for bolt connection. Otherwise, you will need to weld them. So if weld, no holes. If bolted, so there is holes. So for members with holes, if we have one row of holes, so in tension member with one row of holes, the net cross-section area N, is calculated simply as the difference between the gross area A gross minus the area of holes dt. So here is our formula, AN, area net, area gross, the summation of D times T. Okay, so if we look at this, the plan, if we look at this like side view of that, so we will have, this is the thickness of the plate T, and we have this two hole here, and this two hole here. So what is the net area? The net area is the green area here. So this is the net area. So the net area, area net equal to area gross minus each hole is diameter d and thickness t, so 2 times dt. So this is the area net for this case. Okay, so this is how to find area net. And what about area gross? What is area gross based on that? So if this plate B and thickness T, so area gross is B times T. So area net equal to BT minus 2 DT. This is an example of calculation of area net. Another case, so this case is the holes are on the same row, but in some cases the tension member with more than one row of holes, and sometimes we have staggered rows, so they are not on same line, they are staggered. So in tension member with more than one row of holes, reduction in cross-section area may be alleviated by staggering the rows of holes. So this will make it like more efficient, because if you make holes, more holes like that, so the section will be weak. That's why sometimes they use the staggered holes instead of same line holes. So in this case, the possibility of failure must be considered along the zigzag path ABCD. So we have A, B, C, D, E. So this is our line of failure in this case. For the other case, this is our line of failure because they are on same line. So this is the expected line of fracture or failure. But here we have A, B, C, D, E. So when actual stagger SB more than SBM, the staggered holes don't reduce area of the member. So we need to know what is SB and what is SBM. These are the minimum stagger spacing and the spacing. So if we look at the drawing here from this hole to this hole, this is called SG. So this is the, let's say, the vertical, if we have x-axis, y-axis. So SG is the vertical, is the spacing in the vertical direction, and we have SB in the horizontal direction. So we have SG and SB are spacing between staggered holes. Okay. So what we need to do is comparing the actual SB to the SBM, the minimum stagger. So minimum stagger SBM equal to root 4 SG times D, where D is the diameter of the hole, SG is the gauge distance between the rows of holes, SB is the staggered pitch. Okay, so we have minimum spacing SBM equal to 4 SG
Yep.
Yeah. think sometimes it's a problem with the touch screen, so it's stuck and I need to restart the computer again. Okay, anyway, so again, we just need to check the minimum stagger to the minimum stagger spacing compared to the actual stagger. So we have the spacing SB, and we need to compare to SBM, or the minimum stagger. So the minimum stagger spacing SBM equal to the root for SG times D, where D is the diameter of the hole, SG the gauge distance between the rows of the holes, and SB staggered pitch, or this distance horizontally here. Okay, so after we calculate that, if we find that SB more than the minimum, the staggered hole doesn't reduce the area of the member. So this is the first case. So if SB more than the minimum, it's okay, no problem. When the actual stagger SB less than SBM, some part of the staggered hole area H, can be deducted from the member area. So we have two cases. Case 1, SB more than SBM, nothing to do, area equal to area gross. Case number 2, if SB less than SBM, so we need to have area reduced, or we need to reduce the area. So we will have area H equal to dt minus SB squared over SBM squared, or if we replace SBM with root for SGD, so we have area H equal to D times T minus SB squared over 4SGD. So finally, area N will be equal to area gross minus summation area whole of the stagger. So the final formula is this one here, area N equal to area gross minus dt. This is the actual area N. Sorry, this is here. I just need to remove this one here. So in this case, when SB more than SBM, area net equal to the normal area net of the straight line, or the straight bolts, which equal to area gross minus summation dt, or minus the holes. But if we have SB less than SBM, so we need to reduce the area net more by this formula here, area N equal to area gross, area N net equal to area gross minus summation dt plus summation SB square T over 4SG. Okay, so this is how to consider the staggered connection, or staggered bolts. So this is our new area net. Okay, so this is actually what we have to do for the tension member. So for the tension member, again, just a revision. So we have N star compared to phi NT. Phi NT, we need to find the smaller value of these two values, area gross F yield, or 0.85 KT area N times F ultimate. And we have gone through all of that. So another note we have is area net. We have two cases. If we have like straight holes, so area net equal to area gross minus summation delta t dt, sorry, or minus the bolt hole. If we have staggered bolts, so we need to use this formula for area net when SB less than SBM. If SB more than SBM, so similar to the straight ones. Okay, do you have any problem with the tension member design?
Oh, good.
Do you want to have a example on that before proceeding to the comparison? So take one by one, or you prefer to finalize all the procedure first and then go to the examples?
Procedure first.
Okay, no worries. So now we have finished the tension member. So if we go to the next member we have is member subject to compression. So for compression, if this is a member, so the force is pushing the member. So we have NC. So in tension, the force was pulling the member. In the compression, the force is pushing the member. So for just quickly, we have go through this one. So with the behavior of compression member are one of the basic structural element. The structure members carry compressive loads in trusses are called struts. The vertical compression member in building are called column. So the compression member can be called as a column or strut. Strut in trusses and column in normal building. Okay, we have a special case of the compression member, which is called stocky compression members behave in the same way as tension member, which will be failing as a squash load in Y equal to the area times F here. So in some cases, if you have a very thick column and we have the compression force, so because the column is too thick, so it will fail under yielding similar to the tension member. So the value of the force or the maximum force is called in squash load or NY or N yield equal to A times F yield. But this is just a special case for stocky columns. The other case or the normal case is we have cylinder column or cylinder compression members may fail due to two distinct modes of buckling. So we have normally the compression member will fail due to buckling. So we have overall buckling, cylinder column, or we have another mode of failure, local buckling, which is for cylinder plate elements. And in some cases, we have interaction of these two buckling mode. Okay, so as you know, like if we draw it here. So if we have a thin element under compression, due to the cylinderness of this member, so this column will buckle in this direction as an example. So this is the column. So this is called buckling of columns. So usually the compression members are subjected to buckling. We have two buckling modes or two buckling failure modes, overall buckling or local buckling. This type, because it has happened for the whole length of the column, that's why this called is overall buckling or global buckling. Can be also called global buckling. Okay, can we face this in tension members? Do you expect that in tension member? Any idea about that? Have you said anything, William? I couldn't hear you.
Oh no, sorry, I was just looking.
Yeah, I just see your the mute
Yeah.
was yeah.
I think the member will bend, but it's yielding, isn't it, in tension like it would
Yeah, for
not.
tension. Yeah, for tension, it is impossible to happen buckling because when you tension pull this member, so it will only crack or yield. The section may be reduced a little bit or has some nicking, but it will not buckle. So, sorry. Like just if you have, so it will have maybe some nicking due to elongation and then start to crack here, but no buckling in tension. That's why when we design tension member, we didn't consider any buckling. But for this case, for the compression member, we need to consider buckling because buckling is crucial in the compression member. Okay, so can have a look on this figure here. So this is the overall buckling of compression member. We have three different type of overall buckling. We have flexure buckling, this type of buckling. And this one involves like transverse deflection of the members where the blade's junction no longer remained in the initial position. So at the middle, for example, the member has moved laterally. This called is flexure buckling. Okay, another type is flexure torsional buckling in columns. This is similar to flexure buckling, but twist rotation to the cross section also occurs, can be also known as lateral torsional buckling in beams. So this one has lateral movement and also twisting. That's why it's called flexure torsional buckling. The torsional buckling involves pure twisting rotation of the elements, like for example, this member like that. After buckling, it become like that. So there is no transverse movement, only twisting. So these are three types of buckling and can happen like along the whole length of the member. That's why it's called overall buckling, not in some location of the column, but on the on the length of the member. So that's why it's called overall buckling. So this is some example of the flexure buckling and flexure torsional buckling. This one in beam and this one in column. Okay, so this is some example. The second type of buckling or the second mode of buckling is the local buckling. So this local means it happen at special or some specific location of the member. So local buckling of blade element doesn't mean collapse of the member, but it just like it's called deformation of the element at some points. Significant post-buckling strengths present before yielding and collapsing of the member. So this could happen before the yielding or the collapse of the member. For example, this here, so we have buckling in the web of this C-section at some location. Here also we have buckling in the web in the I section. Here we have buckling in the webs and buckling in the flange. If the local buckling of the blade occur, member cannot reach its capacity as the full width of the blade is not effective. So this is the idea here. So buckling cause the member to fail before yielding. So if the member buckles, so it will not reach yielding because the member lose its strength. In the cylinder standard, blade element is considered locally buckling when the actual cylinderness ratio, lambda E, more than the blade cylinderness ratio, lambda E yield. We will see this later, but this is when to consider the member buckling, the local buckling of the member. For cylinder section, local and overall buckling may occur simultaneously, so you can have global and local buckling at the same time. So for example, here we have like lateral movement and also buckling of the web. So we have lateral displacement and local buckling. So it is a mix or a combination of global and local buckling. Here is an example of the local buckling. As you can see here, the whole member is okay, but at some locations of the bottom flange, we have local buckling. So this is an example, real example of the local buckling. Here as well, in this flange here, so we have local buckling. Okay, so this is some discussion about the compression member, and now we can proceed to the procedure on the Australian standard. Here, the design of axial compression is in clause 6.1 in the Australian standard. For a concentrically loaded member subject to design axial compression in star that should satisfy both two conditions. N star should be less than phi ns, and N star should be less than phi nc. Okay, again, if we have a member under compression, so we are looking at the member where the normal force N star is the applied force, and it is applied at the centroid. That is why it is called concentric loading, not eccentric loading. Okay, so we have two. One of them is called section capacity, and the other one is called member capacity. So NS section capacity, NC member capacity. So you should satisfy these two conditions. N star less than or equal phi NS and phi NC, where phi is the capacity factor. You can find it in table 3.4 in the Australian standard, and phi for most of the design calculation of the steel members is 0.9. For the connection, it's 0.85. But you can have a look on this table to find it. NS is the nominal section capacity determined according to clause 6.2, and NC is the nominal member capacity. So again, NC and NS are section and member capacity. So NS is the section capacity, means resistant against local buckling. So the local buckling is represented by section capacity, and NC resistance against overall or global buckling. So the member capacity is related to global buckling, the section capacity is related to the local buckling. Let's start with the section capacity NS because it is easier. So NS is the nominal section capacity of a concentrically loaded compression member equal to this formula here. NS equal to KF times AN times F yield. Okay, so the section capacity depend on yielding. So the section capacity, the failure expected in this case is the yielding. So what is the parameter of NS? KF is called the form factor. KF equal to area effective over area gross. So AE over AG. Where area N or area net is the net area of the cross section, similar to before, area net equal to area gross minus the holes or summation dt. Area effective is the effective area, equal to summation B effective times T, where BE is the effective width. So again, area effective is equal to summation B times B effective times T, where BE is effective width. Area gross is the gross section area of the section, similar to the tension member. Area E shall be calculated from the gross area by summing the effective areas of the individual elements as specified by clause 6.2.4. So here, B effective is calculated based on the slenderness ratio of the members. Okay, so we need to find the effective width to find the effective area AE. So the effective width BE for flat plate element equal to this formula. So BE equal to B times lambda EY over lambda E, and should be less than B. So B effective all the time should be less than B. So the effective length can't be more than, sorry, the effective width can't be more than the actual width. So B effective actually should be, in most cases, less than or equal B, and usually less than. Okay. The effective outside diameter DE of a circular hollow section of outside diameter DO or D naught shall be the lesser of these two values. Take the lesser of. So this for square hollow section. If you have D outer, so D effective will be this one of these two values. So this only for square hollow section. Sorry, circular hollow section. Where? So we need to find lambda E and lambda EY. Lambda EY is element yield strength limit from table 6.24. So let's have a look on this one here. From this table here. So the blade element slenderness ratio, lambda EY, from this table. So depending on what is the member you are designing. So if you have flat plate, so we have longitudinal edge supported one or both. So what are the type of the member we have? We are dealing with hot rolled section. So HR. So hot rolled we have here or here. So lambda EY can be 16 or can be 45. So one means, for example, if we have, for example, a C section, so the flanges are supported only from one end and the other one is free. So for the flange, we have HR equal to 16. So those for the flange. For the whip is supported from the two ends. So this for whips, this for flange. For whip, lambda effective is, lambda EY is 45. Okay, so this is how to use the table if you have a circular hollow section. So use point like 82, sorry. If you are using a different type of steel like cold formed or lightly welded longitudinally, you can use the different value. So here, lambda EY equal to 16, lambda EY equal to 45 for flanges, for whips, if we consider a hot rolled section. Okay, So what is lambda E? Lambda E is the effective slenderness or the slenderness ratio, is the strength of the compression member, is reduced if plate element slenderness exceeds the element yield strength limit epsilon EY. So why we need to know lambda E? Because when lambda E exceeds the yield, this means that we need to reduce the strength. Okay, so when the slenderness exceeds the yield slenderness ratio, means that we need to, or what will happen to the behavior, the strength should be reduced. Okay, because this means the member is susceptible to buckling. So this means the member will be susceptible to buckling. Okay. So how to find the element slenderness lambda E? Lambda E is equal to this formula for flat plate, which we are dealing mostly with. So lambda E is B over T root F yield over 250. So because we have two values of lambda E for flange and for web, so we will need to find lambda E flange and lambda E web. Okay, so B flange over T flange times F yield over 250. Here also B web over T web root F yield over 250. So this is how to use this values. Where again B is the clear width of the element outstand from the support. So this is the width of the flange or the depth of the web. T is the thickness of the blade, or mean thickness of flange or thickness of web. The slenderness lambda E of a circular hollow section can be calculated using this formula. So the special case only for all the steel section is the circular hollow section. Okay. So after we calculate lambda E and lambda E, Y. So if lambda E more than lambda EY, this means B effective equal to B and area E is equal to area gross. So the entire width of the member is effective and the local buckling will not occur. So this is a special case. If lambda E less than lambda E yield, so local buckling will not occur. Okay, do you have any question, guys, about that?
That's
No.
okay. Thanks.
Thank you.
No worries. So now, after we find in S, so we can find phi in S. So the next step is to find in C. Okay, so just to quickly return back to the initial formula here. So we will have, after we get area effective, we divide by area gross, so we can find KF or the form factor. So using area net and KF and F yield, you can find NS. Okay, so this is the first term of the calculation, or the first part of the calculation, phi NS, or the section capacity of the member. The second part is the nominal member capacity in C. So number 2 is phi in C, or the member capacity. So for the member capacity in C of a constant cross section subject to flexural buckling, NC is equal to this formula, NC equal to alpha C times NS. So the member capacity is related to NS. And the maximum value of S, or the maximum cap of it, is NS. So NC cannot be more than NS. Should be less. Okay. Where in NC depends on the slenderness ratio. Sorry, the slenderness of the member, LE/R, and section type. Local buckling may also reduce the section capacity incorporated in KF. So NC depends on the slenderness of the whole member and the section type. Okay, so if this is our member, so we have LE is the effective length, we'll know how to find it, and R is the radius of gyration of the member. So this is one of the properties of the member, and the other factor is section time. Phi NC is the member slenderness reduction factor, function of the modified member slenderness lambda n, and can be determined using one of the following. So we can use it by chart, sorry, by equation, or by chart, or by tables. So to find NC, we need to find lambda c. So using the equation, it is a little bit complicated. So lambda c, to find it by the equations, this equation from the standard. So we have alpha c equal to epsilon times 1 minus root 1 minus 90 over epsilon or zeta lambda. So we have this one is unknown and this one is unknown. So to find zeta, you need to use this formula. We have also lambda here and eta. Okay, so all the calculation depend on that. So the first step is to find, this one is the first step, find lambda equal to lambda n, where lambda n equal to this formula. So if we need to just order them, so we need to find, the first step is to find lambda n equal to that. L effective, R will be known, KF if yield. Then after we get lambda n, we can find alpha A here. Just second step. 2100 lambda n minus 13.5 over lambda n square minus. So after you get lambda A, sorry, alpha A, sorry. So you can find lambda here equal to lambda n plus alpha A and alpha B. Alpha B will come from this table, from table 6.33 and 6.332, 331 and 332. So after you get lambda, you can find then zeta, and then after zeta, you can find, sorry, eta, this one here, sorry. And then after eta, you can find here zeta, and then finally you can find alpha c. So again, it is a bit complicated, so we don't have to use the equations. Another option to find lambda c is from the tables and the chart. Okay. So here for this chart, we have on the horizontal axis modified slenderness lambda n. So we still need to find lambda n equal to L over R root F yield over 250. And then from the table, you can find lambda b, one of these values. So using lambda n and lambda b, for example, if we have lambda n equal to 100, just an example, and then you have lambda b equal to 1 in the middle here, 0, for example. So you intersect with this one here. I select this one, just an example here. So this is 0. So if alpha b equal to 0, so this is our chart, our plot. So if we go horizontally from this point here, the intersection point, so this is the value of lambda c, where lambda c equal to nc over ny. I think this is much easier. The other option is table 33.3. So directly here, using the value of lambda n and lambda and alpha b. So to get into this table to find alpha c, you need lambda n and alpha b. So for example, if we have, as we mentioned, lambda n equal to 100 in the chart. So this is our values here. So at alpha b equal to 0, this is our alpha c. So alpha c, for example, here, 5.541. Okay. So this is alpha c, how to find alpha c. And this is here alpha b table. So let's have a look on alpha b. Values of member section constant alpha b for kf equal to 1. And the values, the other table is for alpha less than 1, kf less than 1. So you know kf, if you have kf equal to 1, or not equal to 1. So we have two tables for the value of k alpha b. So depend on the value of kf, the form factor. So if kf equal to 1 or kf less than 1. So for example, if kf equal to 1, for hot rolled UB and UC section, alpha b equal to 1. So alpha b equal to, 0 when we have hot rolled and UB and UC section. UB again is the universal beam section. Universal column section is called UC. Okay. Another case, if you have the flange more than 40 millimeter, UB or UC, so alpha B equal to 1. So based on what is the type of section you are dealing with or you are designing, this is the value of alpha B. Okay, so again, using alpha B and lambda n, we can find the value of lambda C, alpha C, sorry. And what is the use of alpha C? Alpha C will be used to find the member capacity in C. So alpha C times NS give us NC. Okay. So this is how to find the member capacity. But before we proceed, we have an important part. So when we calculate lambda n, one of the parameter was, if you go to lambda n here, because we need lambda n to access this table. So lambda n equal to L effective divided by R times root KF times root F yield over 250. So here, lambda n equal to L effective over R root KF root if field over 250. So what is the parameter needed here? So if field is known, okay, so we need L effective, R, and KF. L effective is called the effective length of the member, which is equal to KE times L, where KE is the member effective length factor and L is the actual length of the member. LE over R is called the geometrical slenderness ratio, where R is the radius of gyration of the section. So we need to know LE and R before and the KF before proceeding to the calculation of alpha B and alpha C. So KE depends on the rotational and transitional resistance at end of the member, and it can be determined according to these 3 or 4 cases. Okay, member with idealized end restraint, or using appendix G for braced member, or this close for sway members, and this close 4.6.35 for member in triangulated structure. So we will focus on the first one. So using the idealized end restraint.
Oh,
So the
Ahmed,
idealized.
sorry
by the
to
way.
interrupt. I'm not sure if it's just me. It's stuck on, I think, page 15, or if you're writing, I can't see anything.
Okay. Do you see other guys
Yeah,
have you?
I can see that now. Yeah.
Okay.
Yeah.
Sorry.
Thank you.
So everyone can see the screen now.
Yep.
Yeah, yeah.
So there is like various method to find the value of KE. Again, KE in general is if we have a column. KE, we have different buckling modes. So KE is the factors that give us the buckling length of the member. For example, if we have this member here, so this is L effective, so L effective equal to KE times L. In this case, because the buckling happen all over the whole length, so KE can be 1. So this is the idea behind the buckling factor KE. So KE can be found for idealized end restraint using this table here, based on the end restraints of the column. So first of all, we have 2 types of columns, braced member or sway member. Sway member means on braced members. So braced members, we have 3 cases. If we have fixed, so also we have 3 types of or 2 types of support in for column for braced. So for braced column, we have fixed end or bend end. Okay, so fixed end or bend end. So we can have like a combination of the top and bottom end, 3 cases. Case number 1, we have fixed column. So if we have fixed column, so how much K effective? 0.7. If we have top as bend, bottom as fixed, so 1 fixed and 1 bend, so K effective is 0.85. The third case is if we have both of them bend, which is the case here on the left, or the ideal case. Here K effective equal to 1. So
Yeah, Ahmed, I think it's not annotating again. I'm following what you're saying, but there's no writing. If you're writing, it's not coming through.
it's frozen again.
Yeah.
Okay, so also balance it same. So others, are you seeing what I'm writing?
No.
No.
No, I can't see.
So there is some. I think there is some delay. Can you see now?
Yep.
Or yeah. So I think there is a bit of delay between us. So what is the latest thing you are seeing now?
Oh,
The
you just got,
bin-
yeah, the annotation where you got the fixed and pinned supports, and you've just started to go across to the sway members.
Okay, so I will stop the recording and maybe. Okay. So again here, so we have again just a quick revision. We have K effective equal to K sorry, L effective equal to K effective times L, where K effective can be 1 or 0.85 or 0.7 for raised column based on the ends. The other type of columns we have is unbraced column. For unbraced columns, we might have two new supports, which is one of them allowing for translation or movement, but preventing the rotation. Or another one is called free. The free means it allow for translation and rotation. Okay, for this two cases, we have another combination, different combination for the unbraced or sway members. If we have a sway member fixed at bottom and allowing translation only at the top, so the value of KE is 1.2. If we have free at the top fixed at bottom, we have 2.2. If we have bin at the bottom and allowing for translation only at the top, so we have 2.2. So from what we have discussed now, we have to know, we need to keep in mind that K effective for unbraced all the time more than 1, and for braced K effective less than 1 or less than or equal to 1. Okay, so this is the first method of calculating the effective lengths of the columns using the idealized end restraint. Another option is what we have done last week or the week before last week for the members, using these two charts for braced and sway members. Do you remember this one? So we have connection between the rafter or the beam and the column. So we have to find gamma equal to summation I over L for column over summation beta effective I over L for beam. So we have, if we have a column, we have two ends, top ends and bottom end. This is just to decide, so we have to find gamma top and gamma bottom. So this method, because actually in real life, we don't have pure fixed or pure bin or pure translation allowed and rotation prevented. So if you want to exactly find the values of the K effective values, so you need to find gamma for the top end, gamma for the bottom end, and then using the table for the plots, for example, here for braced member. For example, if we have K effective, gamma at the bottom, like 0.5, for example, and at the top also 0.5. So this gamma bottom, this gamma top. So this would be our value. So this graphs or these plots are the value of KE. So here KE is between 0.7 and 0.65. So we can take it as 0.67, for example. So the effective value here, or the exact K effective value, is 0.67. Have you used this formula in the assessment or not yet? Or have you?
Yes, I think we used it before.
Okay, that's good. Any other one have like viewed the previous lecture or have used this formula in the the assessment?
I've used it in a previous unit. I didn't use it in the assessment though.
I haven't used it in this assessment.
Okay, but I think we have discussed this in lecture 2, I think. If you remember or you don't remember.
What was that? Sorry.
Do you remember we have discussed this before in lecture number 2? Have you?
Yeah, it's in the unit
Yeah.
content. I'm pretty sure from an earlier week, but yeah, I thought in the assessment it gave us already the effective length. We didn't need to calculate it.
Oh yeah.
I could be wrong. Yeah.
Okay, but I mean you have like seen this before on the previous module, right?
Yeah. Yeah.
Yeah. Okay. So again, just to quickly gamma, this one gamma, because we have a connection between beam and the column. So the standard give us this formula to account for the stiffness or the size of the beam to the size of the column. So gamma equal to summation I over L for the column divided by summation beta effective I over L for beam. If we like take, for example, for simplicity, beta effective equal to 1, so and we have one beam and one column, so it will be gamma I over L for column divided by I over L for beam. So if you know I for column, L for column, I for beam, L for beam, so you can find gamma. Okay, so you need to do this for the top and for the bottom. Okay, so here also the value of beta, how to find the value of beta. Beta is equal to 1 in braced or sway if rigid connected to a column. So if the rafter or the beam rigidly connected to the column, so we can take 1 beta as 1 and for the sway also beta as 1. Okay. So after all of that, so now just summarizing, so we have again finally these two. So we have n star compared to phi ns and n star compared to phi nc. So look at this is local buckling criteria and this overall buckling criteria. So the first step is to classify the section, flange and web. So we need to find lambda e for flange, lambda e for web, and compare to lambda ey flange and lambda ey for web. Okay, then calculate the plate slenderness lambda e. Calculate lambda, compare lambda e to lambda ey. If lambda e less than lambda ey, so no reduction in the gross section area because no buckling or no local buckling occur. So n is equal to an f field. If lambda e more than lambda e effective, so n is equal to this formula kf times an times f yield. Okay, so this for ns and lambda n star should be less than or equal phi ns to be safe. This for member section capacity. For member capacity, we need the first step to find LE over R to find lambda n, which equal to LE over R root KF root F yield over 250. So find lambda n, then alpha b using alpha n and lambda n and alpha b from tables. You can find alpha c. So all our calculation for the member capacity is to find how much alpha c. So then find alpha C from the table. We will not use the equation because it takes consuming time. So we'll take it from the table. Then after we find alpha C, we can find NC. Okay. Is there any problem with the compression members?
No.
Good. So we have for compression member a little bit more effort compared to tension because the compression member are susceptible to buckling. So the next types of members is the member subjected to bending. What is the member subjected to bending? Mainly beams. Beams or rafters are mainly under bending. So for main beams, beams are carrying loads from floors or other beams to columns. So the beams transfer the floors or the roof load to the columns. Secondary beams are beams transferring loads to main beams, or in some cases, merely for providing lateral stability to the columns. Beams may be cantilever or simply supported or fixed in. So the beams can be simply supported or cantilever and so on. Main function of beam is to support floors. We have also some varieties of the cross section of the beam. So we can have universal beam, UB, compound beam, channel, and crane beam, purlins. Mainly we are focusing on the UB, or in some cases we have a WB. WB means welded beam. It is same, almost same shape of the universal beam, but with bigger size. Okay, most of the beams are not solid, but have material distributed efficiently. Open thin wall section are cheaper because of what weaker in torsion. Hot rolled beams are most used. This is our focus. Hot rolled beam may be compounded with plates. So if you need to increase the capacity or the strength of a hot rolled section, you can weld or bolt some plates, more plates to increase the capacity. Okay, the most widely adopted section in buildings is universal beams. So the universal beams is the most ones. Okay, let's look at the failure modes because the design are mainly depending on the failure mode. So it's good to understand the failure modes. Beam may or may not reach its full capacity, full plastic capacity during failure, depending on the few factors which affect the type of the failure mode. So in some cases, the beam fail before reaching its capacity, its full capacity, due to buckling. Because the buckling will cause the member to fail before reaching its full capacity. Types of failure modes: VS factor versus the factors. So we have plastic failure. This will happen in the compact section with no lateral torsion buckling. So this is the only case the full capacity achieved. So when the member or the beam failed under plastic failure, this means it reached its full capacity. Flexure lateral or lateral torsion buckling, LTB. So depending on the length and availability of lateral torsion buckling or slenderness. So the member can fail or the beam fail due to lateral torsion buckling due to its long length. So if the beam is longer, so it is more susceptible to lateral torsion buckling. Because the member is long and cylinder, so it will fail under lateral torsion buckling, not only yielding. For local buckling, local plate buckling of compression flange, in some cases, because in bending, what happened in bending? In bending, sometimes, if the moment like that, so the top flange is under compression, and What happened to the member under compression? Buckling. So the top flange failed due to buckling. This happened due to compactness of the cross section related to the geometry. One of the modes also of failure is web shear buckling or web shear yielding. This happened due to the thickness of the web. Also, in some cases, if the web is too long or too high, so the web itself buckle due to shear. So this is the web buckling. So this mode of failure is called web shear buckling due to the thickness of the web. So the web is high and the thickness of web is small, so that the web buckle. Another option is web bearing or yielding crushing and web buckling, local failure. This mode is quite similar to the top one, but not the full length of the web buckle, just part of it. So for example, something like that. So most of the web is still straight, but part of it buckle, which is local buckling or web crushing. Okay, these are some examples of the failure modes of flexure members. So this is what we was talking about, like web bearing or web crushing. Here, local buckling in the top flange or local buckling in the compression flange. Okay, and here, if you can see here is web shear buckling, and this one here, number C, is lateral torsion buckling. Okay, so as you can see here, if we zoom out, so this is the lateral torsion buckling of the flexure member. We can have a look on the flexure theory, and then let's jump to the design of member subjected to bending. So for members subjected to bending, steel members subject to bending have part of the section one flange half web of I section under compression. So if you have a member or I section for a beam, if we have a beam under this bending, so the moment like that, so part of the section under tension, the bottom part under tension, and the top part is under compression. Okay, so for bending, we have tension and compression at the same time on the section. Steel beams are also suffer from failures caused to buckling modes. So due to the top part under compression, so it has same problems of buckling modes like pure compression member. So we have local buckling of plates, cylinder plates, depends on section slenderness, and also global buckling of member due to cylinder and laterally unrestrained beam. So the beams or the flexure members are also subjected to buckling, local and global buckling modes. That's why when we design the member under bending or under flexure, we have section capacity and member capacity. Okay. If the beam compact and short, neither local buckling or nor global buckling will occur, so this full plastic moment. If so, this again similar to what we have seen in the beginning at the beginning of column design. If we have a stocky member, so stocky members doesn't suffer from buckling, so that's why it will reach its full capacity. Short beams and beam with full restraint can only fail by yielding and or local buckling. So also the short beams will not be subject to global buckling because they are short. Laterally unrestrained beam may fail by flexure torsion buckling or global buckling. Okay, so now let's start for the design procedure for bending moment. Design for bending moment. MX or MY. A member bent about section major principal X shall satisfy the following. So if we have a member, a cross section like that, we have two cross section, two axes, sorry. So we have X axis and Y axis. The moment about X axis is called MX star. And here in this case, X is our major axis because it is the bigger I. So IX is bigger than IY, so it is major. X is the major axis. So to design for MX, we need to satisfy this two. MX star less than phi MSX. This is section capacity. MX star less than phi MBX, which is the member capacity. So MX star design bending moment. So M star is the design or applied moment. MSX is the nominal section moment capacity for bending about X axis. MBX is the section or the nominal, sorry, member moment capacity for bending about X axis. The first, when we have two cases for member capacity, when the beam is fully restrained against lateral torsion buckling, so lateral torsion buckling will not occur, so MB equal to MS. So the member capacity equal to the section capacity if lateral torsion buckling is prevented. The lateral torsion buckling can be prevented by, just quickly here, because the lateral torsion buckling means like horizontal displacement. So in some cases, you can add like supports to the top flange. So this means that no lateral torsion buckling could happen. So in this case, MB equal to MS, or the section capacity equal to the member capacity. But in general cases, we don't have this type of supports. So if the beam is not fully restrained against lateral torsion buckling, we need to reduce the member capacity or the section capacity to this value. So MB equal to lambda M, alpha M, alpha S times MS and less than MS. So MB equal to 2 reduction factor alpha M, alpha S times the section capacity MS. This is the value of the member capacity. If the member bent about minor principal axis, so MY similar to MY. You can just ignore this one now, where MY and MSY are the design bending capacity moment about Y axis, MSY the nominal section capacity about Y axis. So just ignore this one here, because mainly all our problems will be mainly problems about major axis bending. So all the problems we will have only MX. Okay, so let's start with the calculation. of how to find MS and how to find MB. So for the section moment capacity, MSX equal to F yield times ZE, where F yield is the yield stress using the smaller value of the web and flange, because in some steel types or some cross section, they give the value of F yield for flange and F yield for web. So if you have two values of F yield for one member, so you take the smallest value. ZE is the effective section modulus, can be found from the capacity tables. So we will see, have a look on the capacity tables now. The effective section modulus ZE depend on the slenderness section slenderness lambda s. Section should be classified according to the section slenderness into three types. So we have three types of steel section: compact, non-compact, and slender, based on section slenderness ratio lambda s. So the section can be compact or non-compact or slender. Let's see how to define the section to compact or non-compact or cylinder. So the effective section modulus ZE, the moment and shear and bearing capacity of the beam with cylinder plate may be significantly reduced by the global buckling. So the effective section modulus means that we need to reduce the capacity of the members due to local buckling. Depending on the ability to resist the local buckling based on lambda s, the section can be classified to these three members or three types we talked about. And the compact section happen or the section can be classified as compact when lambda s less than lambda sp. So for each section, we need to find lambda s and compare to lambda sp. Lambda sp is a plastic slenderness ratio. So we know or we will get lambda sb from tables, and we will find lambda s and compare lambda s to lambda sb. So we have three cases. The first case, when lambda s less than lambda sb, the section is compact. When the section is compact, so z effective equal to s or 1.5 z. So this means that the section will not be affected by the local buckling, and the section will be able to maintain the full capacity until collapse mechanism form. So this is the first case. The second case or the third case first, when lambda is more than lambda sy. So this is the third case, because the second case will be between these two cases. So the third case, when lambda is more than lambda sy, where lambda sy is the elastic or the yield slenderness ratio. So we will again find lambda s and compare to lambda sy. If lambda is more than lambda sy, so capacity below their first yield capacity due to local buckling. So in this case, the member is cylinder and the local buckling will okay. Okay, and to calculate Z effective for flat plate element in uniform compression, Z effective equal to Z times lambda SY over lambda S. This for flanges of UB and UC bent about their major axis. Okay. The other case for plate element with compression at one unsupported edge and tension or zero stress at the other edge for UB bent about their minor axis, and we mentioned that we are not using or dealing with minor axis in this course or this year, so we can ignore this one. So we have two cases now. Compact section, lambda S more than lambda SB, sorry, less than lambda SB. So Z effective equal to S or 1.5 Z. The other case, if lambda S more than epsilon lambda SY, so Z effective equal to Z times lambda SY over lambda S. The second case is the in-between case when lambda S more than lambda SB and less than lambda SY. So if in the middle, so we will take some interpolation or intermediate uh, calculation between the compact and cylinder. So Z effective in this case will be using this formula. Z effective equal to Z plus lambda SY minus lambda S over lambda SY minus lambda SB times ZC minus Z. This is called interpolation between the two formulas. Okay, so we have three cases of the section classification based on lambda S and lambda SY and lambda SB. So we need to find these three. The first case for compact, lambda S less than lambda SB. The second is cylinder, lambda S more than lambda SY. The third is in the middle, which is non-compact, lambda S more than lambda SB and less than lambda SY. Okay, do you have any question, guys, up to now?
No.
Okay, thank you. Okay, so this is the whole section. If we calculate for the whole section, and the second step is this part here, effective section modulus Z effective for section with different cylinderness. So for example, if the web is cylinder and the flange is compact and so on, so we have to use this part. When a section consists of elements with different cylinderness, apply reductions to cylinder element alone instead of the entire section. Okay, so this is just in case we have section with compact part and cylinder part, for example. Like for example, compact flange, and cylinder web as an example. So you need to find from this formula here. So Z effective will be Z flange times lambda EY over lambda E plus Z web times lambda EY over lambda E all squared. So this if the cylinder, the web is cylinder and the flange is cylinder. Here, if this one happen here, so this case, the flange is compact, so no reduction in the flange, but the reduction only in the web. For the if the compact web and cylinder flange, so we can use this formula here. So the web is still same, but the reduction will happen only in the flange. Okay, so this is just a case of two different classification in one exam. Just before we proceed, just need to know what is the definition of the lambda E and lambda EY and lambda SY. So the plate element cylinderness, similar to before, equal to B over T times root F field over 250. And for circular hollow section, don't need to focus on this one, but just in case, so it will be D naught over T times F field over 250, where B for the web is the clear height of the web. For the flange, this is B, is clear also width of the flange. Okay. Where some of the symbol we need, Z is the elastic section modulus, S is the plastic section modulus, ZE is the effective section modulus, ZC is the effective section modulus of a compact section, B is the clear width of the element outstand from the face supporting plate, T is the element thickness, D naught is the outside diameter of a section, lambda S is the section slenderness equal to lambda E or lambda effective of plate element in cross section with largest lambda E over lambda EY, where lambda E is the plate element cylinderness, lambda EY is the plate element yield cylinderness limit, lambda SY is the section yield cylinderness limit, lambda SB is the section elasticity cylinderness limit. Okay, so values of plate element. So this in table, this table 5.2 is the values of the cylinderness limits. So, for example, if we are for uniform compression member, so we have again HR is the hot rolled section. So we are looking for the hot rolled sections. So if the cylinder under uniform compression, so lambda EB is 9, lambda EY is 16. This for flange of UB and UC section in bending. Okay, so this is the values for the flange and for the web. Compression at one edge, tension at the other. So because the web has compression at one side and tension on the other side, so EB lambda EB is is 82 and lambda EY is 115. So this for the web and this for the flange. Okay, so this is the values we need from here.
Yep.
Okay, so thank you. So this is the value of the, just repeat this part again quickly. So this is the value of the cylinder limits lambda E plastic and lambda E yield. So for uniform compression for hot rolled members, we have EB 9 and E lambda EY 16. So this can be used for flange of UB and UC section in bending. For web, we have compression at one edge and tension at the other edge, because for webs, if we have bending member, so we have the bottom maybe under tension and the top part is under compression. So lambda EB 20 like 82 and lambda E yield is 115. Okay, so this is the value needed for web of UB or UC section in bending. Okay, for the section modulus, you can have a quick read on that, but we don't go in depth in this one. Not much needed to it. And finally, we go to the design of member subjected to shear. So, as you know, again, beams are designed for shear. So the shear are mainly on beams as well. So the beams are under flexure and under shear. Okay. So in shear, the I section flanges are designed to resist the moment. Whips are designed to carry the shear forces due to variation of the bending moment along the span. So for I sections, the two flanges are mainly to resist moments, and the whip mainly to resist the shear. Okay, whips are also required to support bearing reaction loads and concentrated loads. When subjected to such load, the whip can fail in shear or bearing, through yielding or buckling. So also the whip, when the member is under like bearing load, so the whip also is resisting the bear. So the whip is resisting two types of loads, shear and bear. Four possible failure mode can happen to the web shear yielding, web shear buckling, web bearing yielding, and web bearing buckling. So four modes of failure could happen in the web. We here I will only focus on the resistance against shear yielding, and shear buckling. So no bearing required in this lecture. Okay. Let's go directly to the procedure of the design of shear. So for the shear, using the Australian standard, a web subjected to a design shear force V star should satisfy the following to be safe. So V star should be less than phi VV. Again, similar to the three previous types of loading, V star is the applied or the designed shear force applied to the member or to the section, where lambda alpha VV is the shear capacity of the cross section. Okay, where phi is reduction factor 0.9, VV is the nominal shear capacity of the web. The nominal shear capacity depends on whether the web is susceptible to shear, buckling, or not. So if the slenderness of the web is lower than certain threshold, shear buckling will not occur and failure is dominated by shear yielding. So we have two options of failure or two modes of failure. One of them is shear buckling or one of them shear yielding based on the slenderness of the web. So the slenderness of the web decides the type or the mode of failure of the beam or the cross section under shear. So to find the shear capacity of the web, we have two types of web. We have unstiffened web or the web without any addition. So if this our section, so this is the unstiffened web without anything to support the web. So this is our cross section and the beam is extended in this direction. Another is called unstiffened web. The other option is if the web is a bit weak or we have high shear. So one option is to support the web with some stiffeners each specified distance. So the stiffener are some vertical plates like that, repeated each distance. So this will help the web to resist the shear. So the green plates are called stiffeners, and this web type is called stiffened web. So the first case is for unstiffened web. Consider an unstiffened web subjected to approximately uniform shear stress over height, similar to I section and channel section. So case 1, when yielding without buckling. So if the web will fail due to yielding and no buckling, this will happen when lambda EW less than 82. So when lambda EW less than 82, this will make the web to buckle due to yielding, not buckling. When this happen based on the formulas here. When dB over TW less than or equal 82 over root F yield over 250, and the formula we are using will be VV equal to VW equal to 0.6 F yield times AW. So, and this is the maximum capacity or the maximum shear capacity of the web. Okay, the second case, when shear buckling will occur if lambda EW more than 82. This case happen when dB over TW more than the value 82 over the root. In this case, FV equal to FB equal to lambda V times VW less than or equal FW. So this similar to what happened before. We can call this section shear capacity and this is member shear capacity. Where alpha V is this formula, alpha V equal to 82 over dB over dW times root F field over 250 all squared. And given to us here the values dB equal to d1 equal to the clear depth of the web. For example, if this our section, so this is our dW, the clear height of the web, dW. tw is the thickness of the web, so this is tw. VB is the nominal shear buckling capacity. AW is the cross section area of the web. VW is the shear yielding capacity. Area web is the cross section area of the web. So this just repeated. So just remove this one. So the shear buckling in deep section such as plate girder, web may fail by shear buckling. Strength gain is possible with plates in shear when tension field action is considered. So this is some cases of the tension field action which can increase the shear capacity. Critical buckling stress can be increased if stiffeners were added or are added. So the stiffeners are increasing the shear capacity. The stiffened blade can carry more loads after buckling in diagonal tension field developing between stiffeners, similar to A. If the flange contribution is closed, then tension field can spread like B. Failure in girder panels occur when plastic hinge forms in the flange and the yield zone in web, similar to C. Tension field action causes the web to act as diagonal of an in girder truss. This all just you can read this one, not much important. Here is the relation between the shear capacity or the shear buckling resistance and the web slenderness. As the slenderness increase, what happened to the shear capacity? Decrease due to buckling. Shear capacity decrease due to buckling. And here is a failure of web or web failure in shear. So this is an example of the web failure in shear of an stiffened beam. This is the stiffener here, and this is the web, and this is the shear buckling in the web. Okay, this is an example of the stiffening of the web. Web may be stiffened if the web shear yielding or buckling capacity is inadequate. So for example, if you need to increase the shear capacity of the member of the section, you can use the stiffeners. Okay, so this is some stiffeners. The distance between stiffener is A, and so on. So just as this is an example of the stiffener. The idea here is after you use the stiffener, the formulas or the calculation of the shear might be different. So the calculation will be a bit different when we have stiffener, because when we have stiffeners, the nominal shear buckling capacity, VB, for a stiffened web with S over dB less than 3 equal to this formula, where VB equal to lambda V, lambda D, lambda F times VW, and should be less than or equal VW. And this is the value of lambda V when S over dB between 1 and 3, and this is the value of lambda V when S over dB less than 1. Where is S and where is dB? What is S and what is dB? S is the spacing between stiffeners, and dB is the depth of the deepest web panel. So here, if we have an elevation of the beam, for example, so S is the distance between the stiffeners. So this is stiffener number 1, stiffener 2, stiffener 3. The value of the spacing of the stiffener is S. dB is the depth of the web. So if S over dB between 1 and 3, use this formula, number 1. If less than 1, use this formula. Okay. Lambda D equal to 1 when required by this clause. So lambda D can be taken as 1 for end panel without end post. Alpha D and alpha F equal to 1 as a conservative use. So let's take it again quickly here. Lambda V, lambda D, lambda F. Lambda V can be calculated using these two formulas. Lambda D can be using this formula here. Okay. Lambda F can be taken as 1. So we can replace this with 1, and alpha V and alpha D can be taken from these three formulas. Another option to find lambda V times lambda D from this chart. So using S over dB on the x axis and dB over TW over F field over 250, like this graph. So for example, S over dB equal to 2 and this value equal to 150. So if we go up until we reach 150 here, so this is the value. So if we go horizontally, this will be our value of lambda V, lambda D equal to 0.75, for example. Okay, so this is another option to find lambda V times lambda D. Or another option is from the table 51152. So again, if we assume this value as similar to here 150, just an example, and here like for example 2, to 150 here, and 2, This is the exact value, 0.606. So lambda V times lambda D equal to 0.606. And then using V B equal to lambda V lambda D lambda F times VW, you can find, replace this 3 with 0.606 times 1, you can find lambda B. Sorry, VB. Okay, do you have any question for the shear VB for a stiffened web? We can just ignore this part for the combination. You can have a read of this one, but we don't use in this course. So this is interaction between shear and bending moment. So you can use this formula to check for these two cases. You can have a read on that. Okay, and that's it for this module. Do you have any question, guys, for the design procedure of bending or shear and compression and tension parts? Okay, no worries, no problem. Okay, let's have a look on the thanks, Baron. Let's have a look on the examples here. The other file of some worked example as well. I will upload to the system with a recorded video, so you can have a look on them as well. So there are a few examples for the tension member and compression and so on. So I will upload to the system with this recording. Anyway, if we have a look, can you see the screen now? Can you see the tutorial screen?
Yeah.
Well, good. So for the first example here, we have a tension member. Just to quickly have a look. For the second one, we have again tension member. The third one, we have a compression member. Question number 4, we have also compression member. Question number 5, we have flexural member or member subjected to bending moment. Question number 7, shear for unstiffened blade girder. Question number 8, for a stiffened member. Question number 9, also shear. So we have 9 questions, so we can have some example to apply for what we have done already. So let's start with question number 1. For unequal angle, or sorry, equal angle. This is the size of the equal angle, 50 by 50 by 5 millimeter, grade 250, to be used as tension member. It is to be connected by the ends of by welding one leg of the angle to a plate. If the factor of design axial tension is in star T is 100 kilonewton, we need to check the adequacy of the member in terms of the tensile capacity. From the table, area gross is 443. So let's have a look here. So this is the capacity tables. Do you have the capacity tables for steel section? We'll try to share with you if you don't have. So all the properties of the steel section are provided in tables from the Australian Steel Institute and the providers or the manufacturers. So for example here, the angle is given as 50 by 50 by 5. So how much is the area? Can you see the value? So this is the value. So the area from the table the gross area is 443. For grade 250, if yield is 260 and if ultimate is 410. So if yield 260 MBA and if ultimate is 410 MBA. So from the procedure we just gone through earlier, so we have two cases, or we mentioned that we have n star should be less than or equal to phi nt, where nt, two values, area gross times f yield, or area, sorry, point 0.85 kt an times f ultimate. Okay, and we mentioned that we have to pick the lesson. So for yielding, phi nt is phi times ag times f yield. So phi equal to 0.9, area gross 443, f yield is 260, so the value is 103 kilonewton. For fracture, the value is phi t, where phi nt, where nt is this formula 0.85 kt an fu. Phi equal to 0.9, so phi nt equal to 0.9, kt from the table 7.32. If we go to 7.32, so what we have an equal angle to be connected at the ends by welding one leg of the angle to a plate. So which one of them? This one here, because we have one leg of the angle to the plate. So kt in this case will be 0.85 times, so 0.85 times 0.85 kt times area net. How much area net in this case? Do you know how much area net? Do you know how much area net, guys? Because it is welded, so area net in this case will be equal to area gross. So it will be same to area gross, so 443. And F ultimate is 410. So the value is 1,800. So the lesser of these two is not this one, 103.6. So phi nt equal to 103.6 and n star is 100. So we have n star less than or equal to phi nt. So it is okay, safe. Okay. So this is this is an example of a tension member. This is another one for tension member. You can have a look on it. Question 3 is an example of lightly welded I section column subjected to axial compression. So it is a member under axial compression. So we need to identify if the plate element that will buckle locally, calculate the nominal section capacity. If the column is fully restrained laterally to prevent global buckling, optimize the section, reduce unnecessary area without reducing the section capacity. So for this one, it is an example of design of compression member, but like with an idea to find this requirement or satisfy this requirement. So what is given to us in this example? The height of the web is 400 millimeter. The width of the flange is 400 millimeter. Thickness of flange is 20 millimeter. Thickness of web is 12 millimeter. If field of the cross section is 300. So first of all, we need to know that the classification of flange and web. So we need to find lambda E flange and lambda E web. This is the formula. Lambda effective equal to B over T root F field over 250. So for the flange, we need to find how much this distance B. So B for the flange equal to 400 minus 12 over 2. So this is B. The width, the depth of or the thickness of the flange is 20. F field is 300 and 250. So we get that if lambda EF or lambda E flange is 68.59, which is more than for lambda Y for flange 50. So if we go to here, values of the yield slenderness limits, lambda EY. So we have 1 for flange, both for whip, or hot rolled. So here is the trick. It is lightly welded I-beam. So lightly welded, not hot rolled. So if it's lightly welded, so it is the second one or the next one. So how much lambda EY? 50. So if we go up, so lambda E flange equal to 68.59 more than lambda E yield equal to 15. So flange will buckle locally. Local buckling will happen to the flange. For the web, similarly, but the web here is ready 400 and the thickness of the web is 12 millimeters. So lambda E web will be equal to 400 over 12 times 300 root 300 over 250. So 36.51. For the web, we have lambda E yield as 40. So lambda E web equal to 36.51 less than lambda E yield equal to 40. So web will not buckle. So the flange will buckle, but the web will not buckle. So the next step is to find B effective for flange. B effective for flange is equal to B times B effective B times lambda E Y over lambda E. So B 400 minus 12 over 2 times lambda E Y for flange 15, lambda E for flange is 68.59. So the effective width of the flange is 42.43. Because the web doesn't buckle, so B effective web equal to B web equal to 400 millimeter. So area effective will be area of flanges plus area of web. So area web, area flanges equal to this value. So 4 flange, because if we look at the cross section, so we have one, two, three, 4 parts of the flange plus the web. So this flange 1, flange 2, flange 3, flange 4. So 4 times these values plus area web equal to this. So the form factor Kf equal to area effective over area gross. So it will be 0.394. So finally, the nominal section capacity NS equal to Kf times area gross times F yield equal to 2458 kilonewton. Okay, so this is the section capacity. Calculate the nominal section capacity. So we define the section, calculate the section nominal section capacity, and if we want to optimize the section, so reduce unnecessary area without reducing the section capacity. So as you can see here, so this part is not effective and this part is not effective. So if we want to remove this part, so this is be effective of flange. So new width of flange will be, or flange width after reduction will be 2 times BEF web width, because the web doesn't buckle, so it is still B web or BE web. So this 400 millimeter and this is 42.43 millimeter. Okay, guys, do you have any question, guys?
Not regarding this.
You have other question? Okay, go ahead.
It's regarding the assignment. I'm happy to email you if that's easier for you.
Okay, no worries. I think you sent me one question. I have responded to
Yeah, thank you. I've got just
have
more
another one.
regarding
Yeah.
question 2. Yeah.
Okay, no, if you can send me the by email, that's good as well.
All right, perfect. Thank you.
No worries. Okay, if we go to this example for another example for design for compression member as well, to know how to use the tables or the charts for compression member. So it's required to design a suitable universal column section grade 350 compression member subject to a design load axial load of 5500 sorry 550 kilonewton. The buckling length about x-axis LEX is 12 meter and the buckling length about LEY is 6 meter using the design equations and chart and table. Okay, here is the table of the universal column grade 350 and here is the universal column 3550. This for x-axis and this for y-axis. and this is the chart. So we just need to know how to use the chart for design. So if we look quickly here, so what is given to us in star equal to 550 kilonewton, LEX equal to 12 meter, and here in star 500 kilonewton, LEY equal to 6 meter. Here we don't have the cross section, so the cross section is unknown. So we need to find the cross section. If we need to find a cross section, it is not given to us. So we need to go to tables or charts. Okay, let's look at this chart. So what is, oh, sorry, this table first. What is how to use this chart? So how much is the length we have? So here the design member capacity in axial compression phi in C, effective length in meters LE. So these values are sorry. So these values here are the effective length LEX. So how much L effective we have? 12. So if we go to L12 and we go straight down until we find the closest value to 150. So how this one is closest one to 150. So if we go horizontally, what is the suitable section we can use, or what is the section we should use? What is the corresponding section? This one here. Right? So which one? This value here. So for this two information, we need to use 200 UC 52.2. So this is the section suitable for talking about X. Okay, no worries, Baris. So this is the first part. So using L buckling X. Similarly to L buckling Y, but using the Y-axis buckling capacity. So how much is the buckling capacity? 6 meter. So if we go down until we reach the closest value to the buckling or the capacity is this one here, 615. So if we go horizontally, so this is our section. So using these two information, we need to use 200 UC 46.2. So which one of them we should use? We have two sections now. Which one to use? The biggest one. Choose the biggest one. So if we have this type of problems, the final section we use is 200 UC 52.2 to satisfy N star equal to 550 kilonewton, LEX equal to 12 meter, and LEY equal to 6 meter. This is how to design using the, yes, first, the first because it is the biggest one. This is how if we use the tables, okay? If we use the chart, so we have charts similar to, like, actually the chart are drawn using the tables. So if we look at this chart, so this for universal column, 350. Here on the vertical axis, we have phi in C. Here in the horizontal axis, we have L buckling EX. So this for LEX. So how much LEX? It was 12 meter. So if we go at 12, so this is 12. So if we go a line, straight line, vertically. So if we have a straight line. Okay, so if we draw a straight line at 12 meter and go up, so this is our line. How much is the capacity? The capacity required is 550 kilonewton. So for 550 kilonewton, so each one of them is 600, 700, 800, 900. So it's somewhere here. So if we go here like that, so both lines intersect here. So what is the line what is the section we should use? You have any idea? So both of the lines intersect at this curve here. So this is our section. So what is this section is? What is this section is? This one, sorry. So from the chart, use 200 UC 52.2. Because we draw a line at 12 meter and 55 kilonewton. So we draw a line here. And line here. Both of the line intersect at this point, which on the curve, the red curve. So give us to use this one for LEX equal to 12 meter. Similarly, we will do the same for y-axis because we have LEY equal to 6 meter, N star equal to 550 kilonewton. So we'll do the same. At 6 meter here, we go up with a line. At 550 here, we go horizontally with a line. So here is this one here, which is close to this curve. So from this one, we will use 200 UC 46.2, right? So we have two cases similar to the table. So which one to use? This one, the red one, or the purple one? So the final result, use the largest or the biggest. So it will be 200 UC 52.2. Okay. Do you understand the idea? How to use the table and charts?
Yeah.
Okay. Do you have any question, guys?
No questions from me.
Okay, I'm waiting for the question by email you mentioned.
No, all good.
Okay, thanks, Bars. Okay, no worries, Bars. Thank you. You can send me email anytime and I will try to help as soon as possible.
Yeah. Thank you. Thank you so much.
Thank you. Thank you. Do you have any question, Bas? Could you please share the PDF? Yes, sure. Which one? I will try to add all the data. Do you have the capacity tables before, or you want me to add to the course website? This one, the one we are using now, the capacity tables and charts.
I don't have that one. Sorry. If it's possible, could you please share the PDFs for today lecture notes and these tables, please?
Okay, no worries. I will share and share the standard
Because
as
I
well.
couldn't. Yeah, thank you so much. Because I couldn't find the today's lecture note in my profile and also the yes, because I'm doing only these units and
And do not
yeah,
have access
some
to that.
problem.
Yeah.
Yeah, I don't have access to everything. Yeah, some problems, some issues with my profile. So
Okay,
yeah,
no worries. I will do
yeah.
that.
Thank you so much.
No
Appreciate it.
worries. Thank you so much. Thank you for attending today, and see you next week, guys. Thank you.
Thank you. Yes, see you. Thank you.
Thank you. Have a good night.
You too, Nicholas. Thank you. Thanks, Boris. Thanks, Nicholas. See you.